Hello everybody. Okay, so in this video, we are looking at collisions. More importantly, this video we're looking at direct collisions. So there are two types of collisions that we study in applied maths. There's a direct collision and then there's a oblique collision. So a direct collision is just two objects colliding directly in a straight line, right? So they move in the same line before and after collision. And then an oblique collision is when they meet at an angle to each other. So a direct collision, to read here, a direct collision takes place when one sphere bumps into another sphere. These spheres are moving in the same line before and after collision. So we need two formula to help us solve problems with direct collision. So there are many things we could be asked. We could be asked to find the velocities after impact. We could be asked to find the coefficient of restitution. We could be asked to find the coefficient of restitution in terms of like u and v. We could be asked to find the velocities in terms of the coefficient of restitution and u. So we just need to be able to manipulate these formulas in a way that the question requires. So this one here. So we need these two like laws, right? So we need Newton's law of restitution. So we kind of met this in the last video, but we met a more kind of simplified version because we were only kind of dealing with one object. Since we're now dealing with two objects, we need to get the relative velocity before and after. And how you get the relative velocity of something is literally just v1 minus v2. So all over u1 minus u2. So you subtract the velocities after all over the velocities before, and that is equal to minus the coefficient of restitution. And then we need the conservation of momentum, right? So what we need to do here. So why these two formula, right? So we know, we know Newton's law of restitution. We learned that in the last video, the coefficient of bounciness, the coefficient of restitution. But the conservation of momentum, so we know like in a closed system, the momentum before is going to equal to the momentum afterwards, right? And what we do here is we create a table with the velocities before, mass, and the velocity after. We then create one equation using the conservation of momentum, and we create our second equation using Newton's law of restitution. And then we solve the resulting simultaneous equation of P and Q, and that gives me my velocities afterwards. So we could also be asked to calculate the impulse and loss of kinetic energy. So if you recall, the impulse is basically just a change in momentum. So it's m times the velocity after minus m times the velocity before. And the units are Newton seconds. So Newton seconds. Mass is kg. Initial velocity is meter per second. And the final velocity is meter per second. Kinetic energy then. So we know the kinetic energy is equal to half mu squared. And the unit for kinetic energy is joules. So we'll look here. So two elastic spheres are made of 5 kg and 3 kg of mass. 3 kg, 5 kg, and 3 kg, traveling in opposite directions, collide directly. The speeds before collisions are 6 meters per second and 4 meters per second, respectively. If the coefficient of restitution between the spheres is 1/3, calculate the speed of each sphere after the collision. So what we do first is we create a table with velocity before, mass, and velocity after. So the velocities before. So always helps to draw a little diagram. Okay. So what do we know about my spheres? They are traveling opposite directions. Okay. So actually, let me just rub these out and draw something better. So they're traveling in opposite directions. So this sphere here is traveling at 6 meters per second. And then this sphere here is traveling in the opposite direction at 4 meters per second. So how do I write this now in terms of like my vector notation? And so it's my first sphere is traveling 6i. because it's going 6 in the horizontal direction. Its mass is going to be 5. So it's a 5 kg mass, and this is 3. After the collision, we don't know what it is, so we say it's equal to P. Then for the second ball, it's going in the opposite direction, it's going left. So we're saying it's minus 4I. Its mass is 3 kg, and after collision, it's Qi. We don't know what it is. So these spheres don't have anything happening in the I component. We usually say them for oblique collisions, right? So we're literally kind of only colliding on like a horizontal plane. So step 2, create an equation using the conservation of momentum. So what we know is m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. So if you kind of just sub everything in here, it's going to be 5 times 6 plus 5 times p. What I like to do is I kind of just prefer, let me put in all the values relating to my first sphere first, and then all my values relating to my second sphere afterwards. And then here it's going to be 3 times minus 4 is equal to 3 times q. So I'm going to be left with here 30 minus 12, which is 18. 18 is equal to 5p plus 3q. There it is there. Now we create a second equation using Newton's law of restitution. So what we know is v1 minus v2 all over u1 minus u2 is equal to minus e. So it's going to be p minus q all over 6 minus negative 4 is equal to minus 1/3. So it's going to be p minus q all over 10 is equal to minus 1/3. P minus q is equal to minus 10/3. Now, I'm just going to multiply across by 3 here because this will help me later. So it's going to be 3p minus 3q is equal to minus 10. So I have now made 2 equations in relation to p and q. Now what we do is we solve these relating simultaneous equations. So I have here 5p plus 3q is equal to 18. Then I have 3p minus 3q is equal to minus 10. I don't have to do anything special now because I can cancel out my q's. So I add these up. I get 8p is equal to 8. P is equal to 1. And therefore, if p is equal to 1, 5 times 1 plus 3q is equal to 18. 3q is equal to 13. Q is equal to 13/3. So, the speeds then afterwards, right? The speeds afterwards, so their velocities after, so v1, velocity afterwards is just 1I. Therefore, the speed is just going to be 1 meter per second. Then my speed after, or my velocity after is 13/3I. And my speed then is just going to be 13/3 meters per second on my second sphere. Find the loss in kinetic energy suffered by the 5 kg sphere due to the collision. So we need my kinetic energy before. So my kinetic energy before is a half mu squared. So we need to look back. What was my initial velocity for my first sphere? And it was 6. So it's a half times 6 squared, which is then equal to just 18. So we know what the mass is as well. The mass is equal to 5. So it's going to be 90 joules. Then the kinetic energy after is going to be a half times 5 times v squared. Be 1 squared. So it's going to be 25/2 joules. So 90 minus 25/2, which is roughly going to be equal to so not 25. Oopsie poopsie. So it's 5/2. So 90 minus 5/2 is just going to be 87.5 joules. So that's how much kinetic energy we've lost. Then the change in momentum or impulse of the 3 kg sphere. So we're looking for the impulse. So the impulse is mv minus mu. So it's 3 times the velocity afterwards, which the velocity afterwards is just 13/3I, minus 3 times the velocity before. The velocity before was minus 4. So the impulse here is, yes, minus 4. So the impulse here is it's going to be 13 plus 12, which is equal to 25 Newton seconds. 25 Newton seconds, that is my impulse. And then what we should kind of realize is, right, that's the impulse on the 3 kg sphere. What about the 5 kg sphere? So my 5 kg sphere should have an impulse of minus 25. So let's have a check here. So mv minus mu. So 5 times 6 minus 5 times 1. 30 minus 5. Nope. Flip it around. Wicked witch. Right. 5 times 1. 5 times 6. Sorry. And then that is going to be minus 25 Newton seconds. Right. So that is a direct collision. So let's have a look here on GeoGebra. Not GeoGebra, sorry. Here. So a direct collision. We have a look here. Can I just restart everything? Right. So here's my 2 spheres. Let's kind of model the problem we were doing there. So my first sphere, I can't really model the problem, right? But if we kind of look here, right, direct collision, bang, right? That is what direct collision looks like, right? Look. Anyway, hope this video was some help to you guys. I'll catch you guys later. Bye.